So I did the Pauli exclusion principle. The official definition is that no two electrons in an atom can have the same set of values for the four quantum numbers n, l, ml, and ms. N is the principal quantum number. It basically states the state of energy an atom is in. The higher the n, the higher the state of energy. L is the orbital quantum number. It shows the subshell or ring you're in. So, subshell, ring. That's a ring. Oh. The magnetic quantum number is the specific orientation of a given energy or shape. I'm not very good at drawing a visual of this, but here's what it is. That's what it looks like. I have no idea what the hell's going on, but that's what it is. Lastly, ms is the spin quantum number. It describes the angular momentum of an electron. So, usually up or down. So, how do I find these values? N is given to me, as it's the state of the atom. How do we find L? L is just n minus 1 until you reach 0. So if n was 2, you take 2 minus 1, and you get 1. And you have L, that's not an L. You have L equals 1. And then since it's not 0 yet, you take 1 again, and you subtract it by 1, and then you get 0. And L is now both 1 and 0. How do I get ml? Well, to get ml, you take every number between the positive L and negative L. So every number between 1, or every integer between 1 and negative 1 is 1, 0, and negative 1. You have 3 different values for your ml in this situation. L. And for 0, every integer between 0 and negative 0 is still just 0. So I guess in total we have 4. To find ms, you don't really find ms. Ms is for every single ml, there is a positive and a negative spin for the electron. So each one of these ones, zeros, negative 1, and the 0 again, splits off into its own positive and negative 1/2. Oh wait, 1/2 and negative 1/2. And you just do this several times. So I want to give a better visual representation because this looks kind of ugly. Say we have an n of 2. So n equals 2. We subtract it by 1 to get 1. And then you have L. L equals 1. And then you take every number between 1 and negative 1, and you end up with an ml of 1, 0, and negative 1. And each one of these has a positive and a negative 1/2. Hey, screw it. Here. Very nice representation. And so, what are the applications for this? You know that for I think we're good.